halves still similar to what you did in homework assignment number 1. First half relatively lower, second half pretty good. Yeah. Second half, most of you didn't lose many points. Yeah. Small number of points. Yeah. First half, you have a few questions. Yeah. So the error mainly focused on a few relatively hard questions. So let me explain these questions. First one is hard. First one, most of you missed that. Only 2 or 3 students got it. Yeah.
So isn't the first?
Sorry.
Shouldn't it be false because that's so the determinant is the determinant of Wronskian?
Correct. That's correct.
For it to be independent, the determinant has to not be 0.
So your understanding. So here, there is an issue of level of details. You pay attention to the, higher level detail, but there is second level. You miss the second level of detail. So let me explain that. So that's something a little subtle. In class, I mentioned a little bit. Yeah, I mentioned this point a little bit, but it's not easy to pay attention to the difference. Here, use this question. I tell you, so why it has the problem. Okay? Yeah. Why it is true? Yeah. Because, just like Max said, this is the Wronskian, no problem, Wronskian. Okay? Yeah. Equal to 0, the equal 0 corresponds to the linear dependence, right? Yeah. That's also correct. Yeah, that's also correct. But let's read the whole sentence, whole environment carefully and try to see where is the real problem there. Yeah. So this one we need to understand in a deep way. Yeah. Yeah. Not shallow understanding, the literal, sentence you can see, but another level of detail you need to know. Yeah. All right. There exist 2 linearly independent differentiable functions, no problem, but I skipped one important information, but you may assume you have that. Actually, we don't have. Yeah. You assume some critical information, but in this question, I didn't give you that piece of information. What's that? These 2 functions are not necessary solutions of PDE. Did I say anything about PDE? I didn't say anything about PDE. That's the difference. That's the difference. Under the PDE environment, solutions of PDE condition and arbitrary 2 functions, they are different. Here you see the point. If you look at the exercise questions, I'll give you exercise question set, right? Did some of you notice there are 2 versions? Some of the questions I didn't say PDE, but some of the questions I said PDE. Two versions. I mean, same question set. So when you study, some of you probably feel I repeat the same question twice. Did you have that feeling? So I may repeat a few questions twice, but actually different. The conditions are different. Yeah. All right, so here. This time, you should be very careful. When you see y1, y2, the first question you need to ask yourselves, are they two solutions of PDE? Oh, sorry, not PDE, sorry, ODE. Yeah, PDE, partial differential. Yeah, ODE, ordinary. Yeah, ODE, ordinary differential equation, not PDE. Yeah, ODE, sorry, ODE. Yeah. All right. So if they are not solutions of some ODEs, we calculate the Wronskian. So Wronskian is a function, right? Wronskian could be a function out of control. A function that can change freely out of control. Because if they are solutions of an ODE, then the ODE control the Wronskian. ODE, so that's a, extra condition. Control the Wronskian. So the Wronskian cannot change freely. Yeah. So here, there is no ODE restriction. Then the Wronskian can change freely. And it could happen that function has a 0 point somewhere, but non-zero other places. All right? Yeah, but let's just give you the possibility. But how to see what I said is correct? I need to give you a counter-example. I need to give you a specific example to convince you. All right, so here, let me give you a simple example to convince you. Yeah. All right. All right. Yeah. Y1, Y2. Yeah. Because here, when I select Y1, Y2, I can select arbitrary functions, right? I do not need to consider these two functions must be two solutions of an ODE. I don't need to consider that. Yeah. So then, let me give you these two functions. Y1 equals a linear function a plus x. This a, some constant to be determined. I have freedom to choose to determine this a constant. Because later I will choose this a to make a Wronskian equal to 0. I use this a to control the Wronskian value to be 0. But the whole Wronskian, non-zero function. The whole Wronskian, still other places, non-zero. All right, so Y2 sine x. Okay, these two functions. Now let's calculate the Wronskian. Determinant a plus x, then derivative of y1, that's 1. Yeah. Y2 sine, derivative of sine, cosine. Determinant. All right? Yeah. It's not too hard. Yeah. Let's calculate it. A plus times cosine x minus sine x. All right? Can we factor cosine x out? A plus x minus tangent x. Okay? Yeah. Cosine already, it can take 0, right? Yeah. But I can also make the bracket taking 0. Okay? All right. So here, I try to make the bracket taking 0 at x equals pi over 4. How about that? Pi equal to 4. Okay? All right? So then, to make 0, I let a equals tangent pi over 4 minus x pi over 4. So equals 1 minus pi over 4. Okay? Yeah. A equals that. All right. So then the Wronskian, now I choose a equals this number. Wronskian 1 minus pi over 4 plus x minus tangent of x. This function equal 0 at pi over 4, right? Yeah, just 1 point. Okay, yeah. But this cosine, you can already see pi over 2, right? Yeah, this cosine also gives you Wronskian equals 0, pi over 2. Yeah. But we can choose appropriate open interval I to cover one of the 0 point, right? Yeah. Choose I, cover one of the 0 point. Yeah. So then the statement is correct. Yeah. On some open interval that satisfies equals 0 at some point, just a 1 point, it's 0. But after this point, nearby other points, non-zero. Okay? Yeah. So if you want to ask you why this sounds different from what we learned in our, theorem, yeah, we have some theorem. The difference is that if they are solutions of ODE or not, solutions of some ODE or not. If they are solution of ODE, then if at 1 point equals 0, then yeah, the whole interval equal to 0. Linearly dependent. So on the whole interval it equal to 0. So this is an important difference. Yeah. In class I mentioned a little bit, yeah, but at that time it's hard to pay attention to this difference at that time. So after I talk about that, then I know I should give you this question. Yeah. Those two or three students got this correct. They may not know this. Yeah. They may get correct by accident. Yeah. Because one student got confused. 0 connect to linearly independent. Non-zero connect to linearly dependent. I noticed one student switch that condition. So then by accident, he got this correct. Yeah. Something like that. Yeah. All right. Yeah. Yeah. So here we have an example. Yeah. But definitely you cannot find ODE so that these two functions could be two solutions of some specific ODE. Yeah. Think about that. Okay? Yeah. All right. Yeah. Oh. Yeah. So this is the first hard question. Second one also relatively hard. The second one, yes, yeah, but many students couldn't see. Yeah, so I also need to explain the second one. Here, I do not ask you to prove it. Yeah, here, for most of you, I understand it's too hard for you to prove this. Yeah. But can you make decision based on your background knowledge? Yeah. Here, we have some background knowledge. Yeah. Sometimes you need to make a decision based on your knowledge. Yeah. Here, that's the case. Yeah, let me explain that. Yeah. All right. First, the first thing, when n equals 2, it's correct. You know that, right? Yeah. So that's no problem. N equals 2. Yeah. Because we did it in class. When n equals 2, this statement is correct. We did it in class. Yeah, the method, yeah, here, let me remind you the method I used. Yeah. The method, yeah, actually some of you also use, yeah, so here, let u, yeah, some of you use this, most of you use this u variable equals y prime. Yeah. Then y double prime equals u times, many students use u prime, but if you use u prime, you need to make sure your u prime means du over dy, not du over dx, dy. Okay? Yeah, that's the so-called y prime. Yeah, do not get confused. Yeah. So that's for some student, you know, when I did grading, they write this. Yeah. Yeah. All right. Yeah. Because in that case, this f y prime, y double prime, this equation becomes to f y u times u prime. Yeah. Here, u prime with respect to dy. Okay, this equals 0. That's the first order, right? Yeah. From this form, you can see, from this form, yeah, look at that. Y, u, yeah, y, u. So here you treat y as the variable. Okay? Y becomes a variable, not function. Okay? You treat y as a variable. U, a function of y. Okay? Then derivative of u. So first order. Yeah. So when n equals 2, we have this method. Here the issue is, can we generalize this result to arbitrary higher order ODE of this form? Yeah. So yeah. So it's interesting. We want to generalize. Yeah. Here. So this question, yeah. We want to generalize. Okay. All right. Yeah. To generalize here, yeah. Based on your knowledge, yeah. The first step, you want to do some experiments to check it. To check it. So how strong this rule could be extended to the general case. How strong? Okay? All right. So to see that, you may consider n equals 3. Can you do this for n equals 3 to feel about how strong the rule is? Okay? Yeah, there is some rule. Okay? How strong it is. Yeah. So this time you consider y prime, y double prime, y triple prime. Okay? Equals 0. Yeah. Yeah. Y double prime, you can bring down derivative order by 1. The question, can you bring down triple derivative by order by 1? Second derivative of u, second derivative of u. Okay? All right? Yeah. So here, let's try another time. Okay? Y triple derivative. Yeah, because that's the dy over dt, oh, dx. Yeah. dx or dt, you know, similar. Okay? dx, dt. All right? Yeah, similar. Okay? All right. Y double prime. Okay? All right. Then, still chain rule, right? Yeah. So we do the chain rule. Chain rule dy over d. Sorry. Not dy. D dt. Y double prime. Okay? Not dy. D. Yeah. Derivative. Yeah. This time chain rule. D dy double prime times dy dt. That's the chain rule, right? That's the chain rule. Okay? Yeah. All right. Now, dy y double prime, we can use this. U prime, and this is u, another u. Then we only need to look at this derivative part, right? Because this is multiplication times u. The multiplication does not change the derivative order, right? Yeah. So let's just look at this time. A product rule. Product rule. So here, what's that? U prime square plus u times u double prime times u. Yeah, how about that? Okay, all right. So now you can simplify. If you like, you simplify. U times u prime square plus u square u double prime. Is it second order expression? Second order derivative expression? Bring down by 1. Okay? Yeah. So for n equals 3, it's correct. Yeah. Yeah. Then for arbitrary n, arbitrary higher order, yeah, then you need more math scales. Yeah. In that one, you need more math scale. But after this experiment, do you feel the evidence is strong enough to make you select true? Right? Yeah, because you imagine, we can do similar things for higher order. Yeah. Just a matter of how do we do derivative on the product of something, right? A product. Okay? Product. Yeah. All right? So we keep doing derivative on the product. Product. Okay? All right? For example, the next round, fourth derivative. So here, let me go one more level. Y to the fourth level derivative dt y triple prime times dy dt, this is just the u. Yeah. All right. Yeah. Okay. Yeah. U, but inside d. Sorry. Yeah. Sorry. This should be y. Yeah. Yeah. D dy triple prime dy dt. All right. So dy. There, the previous one, u prime square plus u square u double prime times u. Yeah. It is a little hard, but we do apply product rule. We can see third derivative is enough. Yeah. For higher, we can use mathematical induction. Yeah. Because we cannot do this forever, right? We cannot do this forever. Yeah. But in this situation, we can apply mathematical induction. That's for the proof. That's if some students, really want to have a rigorous proof, then you need to apply mathematical induction. Because in that one, you only need to apply this chain rule, then product rule, once. After induction assumption, you only need to do this kind of computation just once. It's good enough. Yeah. Yeah. All right. So so you can see sometimes we need to go a little deep. Yeah. We need to go a little deep. Yeah. All right. So the first two questions, yeah, relatively hard. Yeah. There is another one, number 5 also. But number 5 is not, we will see, it's not too hard to understand. Just one point. If you get that point, you can get it. These two, you need to, in your thinking, you need to do a lot of thinking work. Yeah, these two. Yeah. If you have any question, just let me know. Yeah. Also, if you have some quiz 3 questions, yeah, part A of midterm, you can also ask me if you want me to explain a little bit. Yeah. All right. Oh, yeah. Since you asked me why 5/4. All right. Here, look at this f function. Do we say anything about f function? We didn't say anything about f function. This f function could be very complicated, right? In other words, this f is not necessarily a linear function, right? Yeah. So when we need to convert it to linear system, we need 2 requirements. Yeah. So let me give you the 2 requirements. The first requirement, because this is an implicit form. Sorry. This equation, this is a implicit equation. Okay? All right. So in order to convert a linear system, first we need to get explicit, at least partial explicit, like this. Why? The highest order derivative should be represented as this f function. That's the first condition. Okay? First condition. Otherwise, you cannot. Okay? So you have to isolate the highest order derivative term out. Then you can do, that standard conversion way. Yeah. But that's still not enough. Second, this function must be linear with respect to y prime those y terms linear, but not x. X not necessarily linear. Okay, sine, cosine, log, of x, all allowed. But with respect to y prime, each individual y term must be linear. Then the whole system is linear. Whole system is linear. Otherwise, you cannot. So that's all the requirements we need.
Okay. Yeah. I don't know. I guess if you have a suggestion on how to study for these things, because I could look on the internet, I could look at the book. I'm looking exactly at the thing that I looked at in the book, and that was the only thing I could find that was applied to this. Because I don't know where to look to actually study these very heavy conceptual questions.
Yeah.
And this theorem didn't mention linear, so I understand these are detailed,
yeah,
thorough, but I don't know how to get the answer to these questions, and I don't know where to study, so it's kind of
yeah, I understand. Yeah, I mean, this kind of understanding, it looks like too hard to get this deep understanding, right? Yeah, yeah. Actually, let me show you just from our notes. Yeah, yeah. Because if I ask you to go through the, online, it's out of control. How do you know where to find the information? Out of control, right? Yeah. But our nodes, let me see if we have 3B. Yeah, I just open it up. We have this slide, right? Yeah. Can you get information from this slide? Our nodes. First, when we do the conversion, we have this form. Okay? Yeah. We have this form. Yeah. Then the linear or not, our textbook has that. So here I didn't say, actually I should say it. Yeah, but I look at the textbook. Yeah. It has this. This function must be linear. Yeah. And actually, this understanding you can get it not too hard. It must be linear. Otherwise, think about it. You have a y1 square. How can you say it's a linear system, right? How can you say it's a linear system? It's a non-linear. Okay? So that second part, not too hard. Yeah. Just by logic. So you can see it. Yeah. So here, let me tell you how do I design these questions. I look at the notes. Okay. How do I make those questions? Because I cannot just generate those questions from my brain directly. Yeah. Because I need to look at something. Right? So basically, I look at our notes. When I see some properties, first this is an important property. This is useful. Then I make a question. Yeah. Based on this property, I make some question. Yeah. When I see some content in the notes, so then to answer the questions, you also look at the notes. Yeah. It's not easy to find a place, but you can find. Yeah.
Okay, I still don't, because I saw this slide and I looked at the book, and it's still, I guess to me, the way you described is logical.
Yeah.
Ever since I took differential equations, the word linear has been, I still don't quite understand what that means. So to me, that's not really logical. That's confusing because I don't understand. So to make that justification, I don't know how to get to that.
All right.
On that question. So I'm just like, I saw this slide, I saw the book, so I'm having trouble figuring out what I need to study to answer these questions.
All right. So let's go back to another question about linear function. Linear function. I remember in Module 1, we have a place talk about linear, right? Module 1, because Module 1, we need to consider first order linear ODE, and I remember I explained with respect to y, with respect to y prime, linear. I remember that there is a place. That's the place we understand what is a linear equation. Yeah. So if you want to ask me, I can find it somewhere. Yeah. All right. All right. Yeah. All right. So here, I remember it's Module 1. Let me start from part B. Part B or part C, how to understand, how to remember. I remember this place, this shaded thing. Shaded place. Or another place is, Module 2. Module, All right. It's hard to, so here, otherwise, probably Module 2. Okay, not here,
The first place you mentioned
Uh-huh.
Part D module.
Oh, good. All right. Yeah. Thank you. Yeah. First place, mention linear.
But
Yeah.
I'm not sure.
Yeah, here. Yeah. Linear. Why we call them linear, right? Yeah. First, this linear function. All right. Yeah. Then here. Okay. Yeah. Exactly. This place. Yeah. All right. So here we talk about this case. With respect to y prime, it is linear. Okay. You just look at y prime. Okay. You can ignore. Or treat other as the constant. Yeah. Yeah. But I remember, with respect to this, with respect to y, linear, but you cannot have product of y prime and y, right? That's nonlinear. Yeah. That's nonlinear. Y prime times y, yeah, because y prime, y, we both treat as some functions. The product, we cannot call the whole thing is linear. Yeah.
I'm not sure if it's possible, but if possible, could you like write up a simple example of why you can't multiply y by y prime?
What I mean is the y prime, yeah,
Or
here,
to break the
it's nonlinear. Yeah, what I mean is, oh, all right. Yeah, oh, your question. Yeah, I think your question. Yeah, it's a good question. All right. First, oh, yeah, I move something. Yeah. All right. I need some space. All right. Then explain your question. All right. So you asked me. Yeah. So let me clarify. Suppose we have. Let me use example. Oh. Why is that? Oh, yeah. All right. You asked me if we have y prime times y term, then it won't be linear, right?
Yeah.
Okay, good. Good question. Yeah. All right. Yeah, let me do this. Okay. P of x, y equals q of x. Okay? All right. Other terms linear, but this one non-linear. Yeah. All right. Yeah. Y, then we have this product. It breaks the linearity property. Linearity. Yeah. Remember, linear directly connect to the linearity property. Yeah. Here, let me explain. Yeah. You know, Julie's question. It breaks the linearity property. Yeah. All right. What's the linearity property? Linearity property, yeah. If y1 is a solution, yeah, we assume y1 and y2 are two of the solutions. Okay. By the linearity property, y1 plus y2 should also be a solution. Okay? All right. Linearity property. Yeah. Yeah, but here, if you try that, you will see you have trouble. Okay? All right. So y1 prime times y1 plus p of x y1 equals q of x solution. Yeah, yeah. All right. Yeah. Yeah. So here, let me remove q of x, because if we add q of x, automatically it breaks the linearity. Linearity, remember, we need to have it for homogeneous, right? Non-homogeneous already break the linearity. Yeah. Let's just make the homogeneous. You know. Yeah. All right. There, y2 prime, y2 plus p of x, y2 equals 0. Can you see in general y1 plus y2 prime times y1 plus y2 plus p of x y1 plus y2 won't be 0 in general, because this part, you expand them out, okay? You have 4 terms. 2 terms already good enough, right? Yeah. So here, after expansion, let's do expansion. y1 prime, y1. Another, so y2, I put them together. y2 prime, y2 plus p of x, y1 plus y2. Okay? This part. Another 2 terms, y2 prime, y1 plus y1 prime, y2. We know the upper part equal to 0, right? Adding up, the first 2 solutions. The bottom part, usually not 0. Okay? The bottom part, because the product, you have extra terms. The product, you generated extra terms. Then, it breaks the linearity property. Linearity property. So when you have product, okay? Yeah. So so here, I know I need to use very rigorous description. Yeah. Here it's very rigorous description. Yeah. You just get the idea. Okay? Yeah. Any product of y terms, y related terms, break the linearity. Yeah. Any specific, any individual y by itself, it must be a linear function. Yeah. And other, I remember. Oh, yeah, I remember somewhere. Yeah, probably still at D or somewhere. I said, the coefficient of any y cannot contain other y terms. Yeah, I remember I said that. The coefficient of each y term cannot contain any other y functions. Yeah. The coefficient will break the linearity. The coefficient of other y terms would break the linearity property. Yeah. Yeah. That kind of understanding. Yeah. Here, so to get that deep comprehension, you need to familiar pretty much all the materials. Yeah. So we talk about that early. Yeah. Module 1. Yeah. So here we need to use the knowledge from Module 1. Yeah.
Okay, so generally wrap it all together. So basically, if the question had said, just make a system of ODEs, it would be true. But specifically because it says a linear system of ODEs and you don't know the complexity of the given function, and you can't say that it's true.
Yes. Yeah. Good. Yeah. Question? Yeah.
The reason the product breaks linearity, is that because any product of 2y functions you're going to have basically a polynomial of more than degree 1?
Yes, good. Yeah, that's another view. Good view. Yeah, polynomial degree 1. Yeah, what he said. Yeah, he gave us another good view. So each y we treat polynomial degree as 1. So the product actually the degree 2. You add. So let's look at this product. Degree. Let's look at the total degree of this term. Yeah, his view is good. Total degree of this term. y1 prime contributes degree 1. y1 contributes another degree 1. 1 plus 1, 2. Yeah. In that way, it's correct. Yeah, it's correct. That way, we can see nonlinear term easily. Yeah. Nonlinear term easily. Yeah. And for x function only use x variable, we do not count as degree. Yeah, no degree contribution. Yeah, degree contribution 0. Okay. Yeah, but for any y-related y terms, yeah, each y, so how do we call it? Yeah, y, yeah, yeah. Is there appropriate word for it? Yeah, each y or y prime, you know, y something, yeah. Yeah. We counted degree contribution 1, each one. Make 1 degree contribution when we count the total degree. Yeah, so that's a good view. Yeah. Good view. Yeah, yeah. So here, I know most of you do quite well. Yeah, very close to break time. Most of you do quite well in computation questions. Yeah. Yeah. But another side, understanding extremely important. Yeah. So I want you to have a solid understanding. Yeah. Yeah. Especially when you apply theorems. Sometimes you cannot apply theorems. Yeah. You need to really check all the environment factors, you know, the conditions. All right. Yeah, I do not have much time. Yeah, let me go a little faster. Yeah. Yeah. All right. Other questions? Yeah. 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 All right. Yeah, other questions, not too much to explain. Yeah. Not too much to explain, yeah. Yeah, all right. One, this number 14, yes. This number 14, most of you missed the part of it. Yeah. Most of you, I look at most of you stop at this point. Yeah. But those students, they wrote a cosine, sine. Yeah. They didn't write sine, cosine. Yeah, cosine. You know, C1 cosine T3 plus C2. You know. Yeah. So 3. Yeah. Sine. Yeah. Another minus. Yeah, like that. Yeah. One student after that, so that student take, you know, square, sum of squares, cancel out t, but most of you just stop right here. Didn't complete the remaining part. So our goal, we want to get the equation y1, y2. There is no t, y1, y2. So this is equation in y1, y2 plane. Because when we draw trajectories, we draw in the y1, y2 plane. Okay. So we do not see t there. Okay? Yeah. So in the equation, you should not see any t. So you need to get this kind of equation. Yeah. In our notes, we have a similar question. If you look at the notes, yeah, just change 9 to 4. Okay? Yeah. 3 to 2, 9 to 4. Yeah? Yeah. Similar structure. Yeah. Just the number is slightly different. Yeah. And in the notes, I did the similar way. Okay? Yeah. I did a similar way. Yeah. But I saw one student did square sum of square. Yeah. That's also okay. Sum of square of these two functions, then cancel out, you know, then some, you know, identity, sine, cosine identity, then t is gone. All t. So your goal, you want to eliminate all the t terms. just find a way to eliminate t terms. Then you're done. Yeah. Whatever it is, just eliminate t-related terms. Yeah. Yeah. That's the goal. Yeah. So this one, yeah. Many of you missed this question. Yeah. And other questions. Other questions. Yeah. One. Yeah, I see. Yeah, this. There is one. Yeah, this 18. Yeah, this 18. Yeah. Many students apply some formulas in the textbook. Yeah, it's correct, but that part is correct only for particular solutions. Particular solution. We know we have two parts, right? General solution part and a particular solution part. Yeah. But those many students, so they calculate the formula. Okay, yeah, there is some existing formula. Okay, yeah. But that formula after the calculation, that it corresponds to only particular solution, but not general solution part. Okay, yeah. So that's another. Several students did that way. Yeah. Okay. Yeah. Because when they apply the formula, they do not need to do the calculation like this. So here we went through the details of calculation. So those formulas just the end result of the calculation. Yeah. So the textbook has the formulas. So it's okay, you can apply the formulas. But you need to know you only get particular solution. You didn't get a general solution, this part. You need to add it back. Yeah. So that's another relatively common mistake. Yeah. All right, so this one, this number 19, although many students have it, have this one, but I'd like you to pay attention to the unit conversion. Yeah, because here we need to use different unit. cm, centimeter, meter, Newton, kilometer, kilogram, all those units. But keep track of the units carefully. Yeah, because some of the questions, I know in our textbook, there are answers for all the number of questions. Yeah. But I hope when you have those answers, you need to understand step by step. Yeah. For some of the students, they may not understand the meaning of those steps. Yeah. Because too simple. In the solutions in the textbook, it's too simple. Yeah. I need to spend quite some time to understand. I try to recover all the details. Yeah. All right, so let's stop right here. Yeah.